Curious, engaging, watch what happens when three independent beams of light move through an empty void. When they eventually cross paths on the exact same plane, they trap a closed two-dimensional space inside them. This is how we get the most basic building block of all geometry, the triangle. This diagram shows the anatomy of that collision. A triangle is made up of three vertices, the exact points where the lines meet, which we label A, B, and C. Connecting those points gives us three sides, and inside those boundaries we have three distinct interior angles. We name the shape by its vertices, like triangle ABC. But there is a strict spatial constraint. If points A, B, and C ever align into a perfectly straight line, they become collinear. The trapped space vanishes, and the entire shape flattens into a single line segment. Geometry is built upon these intersections. To construct accurate shapes, we have to understand exactly how lines and points interact in physical space. Let's test that understanding with a specific challenge. We want to construct a perfectly balanced equilateral triangle where every single side measures exactly 4 centimeters. Take a look at this digital drafting table. We start by drawing our perfectly straight 4-centimeter base. Then, relying entirely on a ruler, we pivot up from our starting point, guess the correct angle, and draw our second 4-centimeter line. But then we measure that final connecting side. It reads 4.6 centimeters, too long. So we adjust the ruler's angle, sketch it out again, and now the gap measures 3.5 centimeters, too short. This trial and error method fails because a straight ruler can only measure distance in a single linear direction. When you are trying to predict the exact location of a point across 2 dimensions, a simple straight edge leaves you guessing. We need a different mechanical constraint. To fix this, we put away the ruler and pick up the compass. We usually think of a compass as a tool for drawing circles, but its true mathematical function is to act as a tracking device. It locks in a fixed distance and projects it outward in every direction simultaneously. We can use this to execute side-side-side, or SSS construction. In this diagram, we anchor our exact 4-centimeter base, AB. Then we set our compass width to 4 centimeters, place the needle on point A, and sweep a wide arc across the page. This sweeping curve represents a continuous map of every point in physical space that sits exactly 4 centimeters away from point A. Now, we maintain that same 4-centimeter radius, move our needle to point B, and sweep a second arc through the first one. Look at the exact spot where those two curves collide. That single point of intersection satisfies both conditions at once. By placing our third vertex, point C, right there, we guarantee the remaining 2 sides are exactly 4 centimeters long. We removed all guesswork. By using intersecting circular paths, we forced a perfect equilateral triangle into existence. This geometric logic applies to any combination of side lengths. Let's try building a scalene triangle, where all 3 sides are different, say 4, 5, and 6 centimeters long. As this diagram shows, the mechanics remain the same. We lock in a 4-centimeter base. From the left, we sweep an arc mapping a 5-centimeter radius. From the right, we sweep an arc mapping a 6-centimeter radius. We connect our endpoints to the single collision point, and our scaling triangle is complete. If you were to do this using 2 intersecting arcs of the exact same size, the resulting shape naturally forms an isosceles triangle with 2 equal sides. Mapping out distances as colliding arcs gives you the mathematical toolset to lock these fundamental three-sided shapes into existence every single time. We have moved from the frustration of visual guesswork to the precise mathematical logic of intersecting boundaries. Now it is time to test your understanding. Two identical overlapping circles. Circle A's edge passes through the center of circle B, and circle B's edge passes through the center of circle A. Connect center A, center B, and their top intersection, point C. What exact type of triangle is formed? As you work this out, think carefully about what the distance from the center point to the outer edge actually represents for both of these identical circles. Drop your solution in the comments below. Decoding these spatial collisions is the secret to mastering the shapes in your curriculum. Hit the like button, subscribe to Textbook Toonz, and join us for the next episode where we test whether a triangle can actually be built using just any random side lengths. See you there!